And just a quick introduction, folks. Arvind Akela is the Director of Engineering and Environmental Services at Silicon Valley Clean Water. He has 15 years, I'm betting it's more than that, of engineering experience in water and wastewater projects. He's responsible for implementing an array of wastewater projects for sure, but has a keen interest, especially in energy and biosolids. There is a lot of embedded activity at Silicon Valley Clean Water, which you might touch on. He has been instrumental in bringing some of the innovative technologies and solutions that include aeration, dewatering, food waste, codigestion, demand management through energy storage, codigestion of fats, oils, and grease, otherwise known as FOG, safe MBR, kind of a new filtering technology, all kinds of great things. And then because you guys, certainly you have amazing amount of construction, and which we've been following over the years, and I guess you just wanted more projects. So now there's a new. I guess you can tell us about the SF Peninsula Pure Water project.
Sure. Let me share my screen with you. See if we can do this way. Okay. Is that looking better?
Looks good.
Okay. All right. So, whoops. So I'm here to talk about this San Francisco Peninsula Regional Pure Water Project. Earlier speaker just mentioned about, and you asked Dennis about how it looks like there are some connections here. Yes, there are. And that's why what we are doing is connecting the dots or connecting the drops, because we're all talking about water. So a little bit background about why we are doing this, this project. Before I start, Dennis, I just wanted to make sure that the screen that I'm sharing is the full screen.
It is.
Okay. Okay, sounds good. So this project actually started a long time ago. At some point, Silicon Valley Clean Water wanted to explore and had the vision of using a long-term strategic planning for our recycled water. Of course, this started with the original idea of what's going to happen if some nutrient removal requirement comes in through regional board or some other measures. So we should do something about it. So we started taking initiative. We started reaching out to regional partners, and at this point, you can see that we have 7 partners actually involved at this stage, which I will talk a little bit more about in a minute. So over the last 6 years, we have worked with many partners around the San Francisco Bay Area region, more precisely in the Peninsula. But at this point, these are the 7 partners that we have not only been just talking and exploring, but rather we're at a phase where we are getting into memorandum of agreement. Means we're signing agreement to pursue this project. And what that is, I'll explain in a little bit. But at this phase, I just wanted to kind of put this out. It is no longer just exploratory effort, rather it is as a phase of, as a phase where we're developing basis of design report. Means it's becoming a little bit more real. So why are we doing this? I think I gave a little bit of reasoning why SVCW initiated this regional effort back in, several years ago. But at this point, if you're looking at these reasons, I think the main title, or the real title, should be, why are we not doing this? And you can see the entire California, in fact, the West region of the United States is going through record-breaking drought and water shortage. And of course, the peninsula cannot solve the state's water problem, but it certainly can be a part of a solution in solving this big drought that we're facing, and many, many years to come. So if we do not do anything, it is not going to get better. The key here is that the wastewater holds a key to a part of the solution. And that's why Silicon Valley Clean Water partnered with the Peninsula agencies to be part of that solution. We also know that even if it sounds a little bit weird, but we have more housing being built around pretty much everywhere you go. In the last decade or so, we haven't built enough. So while we are catching up, we are seeing that more and more houses are being built. More people are migrating to the area, and hence it's increasing water demand and more water needs. So in order to meet more water needs, we need to have more water supply. Why not tap the water that it's already available? And that's where we're coming into. Nutrient management. We all know the wastewater discharge has some level of nutrient in terms of nitrogen and phosphorus. That nutrient is important for some, but not important for the others, and it needs to be managed. Through BACWA and SFEI, we have been conducting, and we've been part of a study for several years now to research how this nutrient is impacting the bay. Certainly the science has not concluded to that limit, but there's a component of nutrient that can be part of the solution. And doing some sort of indirectable or directable potable reuse, we can minimize whatever the nutrient is in the discharge that's going into the bay. Sustainability. This water shortage is not going to be a one-time issue. We are facing this for the last almost a decade now, numerous years of drought in a row. And this is going to continue unless we find a sustainable solution. We cannot no longer rely on those big snow packs that we always used to in the Sierra Mountain. So why not utilize the water that we already have? After all, it's one water. It's the same water that's circulating through the environment. And then regional approach. Again, the way I connect or give the reference to is the energy grid. Think about how our power grid works. Our power grid is connected not only at the state level, but at the regional level. And we all had experience in the last 2 weeks ago through that severe heat wave, how the power can be imported and exported at the grid level. We can have something similar to at the regional level for water supply. We can have water in and out into the grid or water grid the same way. So why have we not approached that? These are some of the reasons, and I'm sure there are many more that can be explored, why these types of projects are needed. So what are our options? When we started looking at, we had everything on the table. We wanted to explore. We called it PREP, Portable Reuse Exploratory Project. It was basically, let's sit down and figure out what we have available. What can we do? Through these numerous efforts that we did, we figured out there's definitely some regional solutions that we can think of. One is the water that we have available, we can utilize it for groundwater replenishment. That's one solution, not necessarily the best. We can augment the reservoir water, and we have a large reservoir in terms of crystal springs available. So if the water is purified to the standards, then we can augment that. We can do raw water augmentation. I think on the screen you can see there's Bear Gulch there, and that can be augmented by treating the water and storing it there. Then going a step even further, we can put treated drinking water straight into the supply system. So there's all kinds of things available that we can utilize. What type of potable reuse? Again, when we started looking into it, we explored everything. In fact, our list was pretty long. But you can see we had to hone it down to just a few that are more reasonable, and we had to go through the feasibility study. So you can look at, there's surface spreading, basically groundwater recharge. We can do direct injection. Again, I just talked about reservoir water augmentation, raw water augmentation, and treated drinking water augmentation. When we do all of these, we can reach the same goal. But after doing through some of the exercises and workshops and numerous meetings, those two kind of disappeared, and we were left with reservoir water augmentation and raw water augmentation and treated drinking water augmentation. Now, further looking into that, we turned out that the raw water augmentation, which we were considering as a Bear Gulch, wasn't a reasonable option. Again, I'm not going into too much detail, but just a high level of what this project is about. So we're down to reservoir water augmentation, and treated drinking water augmentation means straight into through the advanced water purification, we can supply into the main water supply system. So again, the sources of water, SVCW is located at the end of the Redwood Shores, and we also have San Mateo as a partner, which has a facility in San Mateo. So these are the two sources of water source. What would take to do this project? These are the project components. Of course, the water that will come from the treatment plant will have a certain level of treatment, but then it has to go through additional advanced water purification process. So we will require advanced water purification facility that will take the final effluent, kind of the same quality that we usually discharge into the bay. This will go through this facility. We will need to build miles and miles of pipelines for tertiary effluent and purified water. We'll need pumping stations. So as you can imagine, what we are talking about requires pumping water from almost the sea level to, if we ever do that at the crystal springs, then we have to go through that hill. Of course, when we do this, there's a lot of brines in there that needs to be taken care of, and it could be, it will have to be dealt with. Storage, you have to store water for equalizing or meeting the demands and supplies, and also the seasonal variations. And then potable water system tie-ins, where we do it and how we do it. So those are some of the components that had to be looked into and still being evaluated at a greater depth. I want you to read every single line of this to understand. Certainly not. It's just a depiction of how many different variations of the same alternative we looked into. And this is just 5 alternatives that I'm showing, but we looked into a lot more variations in the beginning to just filter down and screen it and bring down to these 5. And then after that 5, we had to further refine those options to get to the point where we can kind of start going into the level where we are, which is the basis of design report. We had to look at the cost component. These projects are not cheap. And in order to build a new advanced water purification center, pipelines, pump stations, brine discharge, all those components, it will take hundreds of millions of dollars. And by the time we will build a project, it will be probably 5 to 10 years. So we had to look into some cost projections, where we are and where we are going to be. Some of these cost projections that you see here, based on the real numbers that we have this historical rates, and then we have some projected rates. As you can see that the wholesale water is at the low end and the high end. So the cost of water is not going to go down anytime soon. So the better we catch up, the more prepared we are in order to deal with it. So if we start early, we're going to be better off in near future in terms of securing the water supply as well as the cost. Every year we delay, as you can see, as of yesterday, the inflation rate is over 9%. It's not going to get cheaper. So we better get started. Again, this is the cost. These are the cost of raw water augmentation and treated water augmentation at the low and high level. And that's going to be the cost in near future. So if we compare the cost of water, purified water, with today's dollars, it may not be fair. We have to compare this with the year that the facility should be up and running. As I said earlier, we're expecting this to be around maybe at least a 10-year time frame when this facility can be up and running. We would like to get started very soon, but there are a lot of steps that we have to go through. Finding funding and defining the project, meeting all the regulatory requirements. All of those are going to take some time. And based on that, we realized that the earliest we could have this facility up and running would be at least 10 years from now. And in 10 years, the water cost, you can see how that's going to go high based on the projections. So our next step, we're in the process of signing. In fact, most of the 7 partners have already gotten the approval of memorandum of agreements already, including SVCW. We got it approved. We have our next step is to, once all the partners have gotten it approved through their governing bodies, then we're going to issue this task order to Kennedy Jenks, who is going to design and develop the basis of design report. It's kind of a 10% design with the CEQA ready documents. It has to be USBR Title 16 to meet all those funding requirements. We need to develop some public outreach concept. And of course, continue planning with the regional partners. So with that, I will stop, and certainly there are some questions that I can answer. There are some questions that I can't, maybe because just we don't have the answer to. But that's our answer to the severe drought and water shortage crisis that we are going through, and how the regional partners can come together to address this problem. Dennis, back to you.
Great. Thank you, Arvind. This is quite interesting news, and you certainly a lot to think about. And I, just to be clear, when you had that, I tried to read everything on that one slide, but I didn't get through it in time. I guess the plan right now, just say if was going to be the larger volume of water. I think it was So I think it said there 13 million gallons a day, but that would be a potable water solution.
So yes, the capacity of this facility could be anywhere between 6 to 12 mgd, million gallons per day, depending on the demand. So it really depends on the demand and how much the local demand versus the connected demand that we can address. Between SVCW and San Mateo, I think we have a reliable water supply source for 12 million gallons a day of water supply, treated water supply.
Yeah.
If that answers the question.
Yeah, well, that answers the input question, and then on the output, I saw there were some options to go up to the reservoir at 280, but it seems like that option number 6 would be to just directly augment supply on the bay side.
So SFPUC water supply system is basically, they store the water into the reservoir anyway. If we convey that water, the treated water, into the Crystal Springs reservoir, then that would be the storage. That's where, that can be the source for the water whenever it's needed. So it's like a large reservoir that just holds the water until you need it. And then the water supply system will take it from that reservoir on as needed basis.
And actually, this is a scheduling, fortuitous scheduling, because next up we have Mehdi Sanaki talking about RO concentrate management. You'd be making a lot of RO concentrate. So are you committing to work with Mehdi to solve the RO concentrate problem?
Well, it certainly is going to be one of the challenges to manage, and we think we can manage it. Again, this requires not only commitment from us and our regional partners, but also we have to get blessings from the water board. The brine or RO concentrate, I heard that don't call brine, so I wouldn't call brine.
Yes, right.
Let's call it RO concentrate. If we have RO concentrate, it has to go somewhere. Where does it go is a question, and we can manage it. And certainly Mehdi can probably shed some lights on that. But that discharge the RO concentrate could be addressed in multiple ways. One of the ways is to discharge into the bay, but that would require cooperation and collaboration with water boards. But again, this is something that we have to deal with at the time when it comes. But it is one of the challenges.
I've been fascinated. I mean, there's a number of fascinating things about Silicon Valley clean water and just all the kind of things going on. Certainly with the construction, with even some of the embedded projects or companies that are there, Mango Materials, Bioforce Tech. I did also see something about the Fournier presses in terms of dewatering. So I just wonder, within this realm, I mean, the construction and these initiatives. Oh, and Sebastian Tillman's project and the kind of as far as the safe SAF-MBR, as far as that secondary kind of filtration. I just wondered if you'd want to mention any of those in particular.
Yeah, Absolutely. Well, we have, we can take up the rest of your afternoon if I.
We're actually on time today.
So yes, some of the highlights, I would say, if you go at Silicon Valley Clean Water right now, you will see that the plant is torn apart no matter where you go, because construction everywhere. And that's because we are, doing a lot of work. Some of the ones that you mentioned, but I do want to highlight one of the very, very recent ones is we have been working on organic codigestion, or AKA food waste codigestion project for a while. And we started doing that since 2015, and we have conducted pilot. We have gotten grants from California Energy Commission to conduct the research. We completed that research. We published the report. We continued working on that, and then very recently we submitted a grant application to Cal Recycle, and we just last week we received a $4 million grant to expand upon our codigestion project. So we are going to increase the capacity of codigestion that we are doing right now, especially the organics codigestion or food waste codigestion that most people refer to. In addition to that, we do have, Biofirst Tech that, takes our 20+% biosolids, converts that, dewaters it and converts that into biochar. That facility is, certainly running. SAF-MBR is a pilot facility. Again, it's a 100-year-old concept we have right now for the secondary treatment, which is through aeration and activated sludge system. That is very old system, but it's also the most energy intensive process at a activated sludge treatment plant. SAF-MBR takes that secondary process, plugs itself between the primary sedimentation, primary treatment and the tertiary treatment, and that's your plug between those two, and actually has the potential to make the plant as a energy neutral. And it has conducted its research. It has, this was another California Energy Commission grant project. We completed it, and the concept has been proved that yes, it can be net neutral facility. So that's, Fournier press you mentioned, that is another a good technology that we utilized. We had centrifuge, basically a 200 horsepower motor, spinning it so fast to squeeze all the water out of our biosolids. The Fournier press reduces that 200 horsepower down to 40 horsepower. So it's a huge energy savings that we are experiencing because of that process, and it is able to produce 22% solids, biosolids. There's many other technologies that I can continue talking, but I know you have some time limitations, so I'll stop right there.
We will look forward to keeping track of all these things, and having you back for because there's many stories to tell. Just with all the things you're doing, and congratulations on that organic, that food waste codigestion. Just in terms of inputs and outputs here, what is the food waste input?
So currently we are taking about 20 tons per day. When I say 20 tons, means 6 dry tons and 20 tons at 30% solids range per day. Our goal is to go to double, or maybe more than double the capacity. So the grant would help us expand the facility so that we can start taking way more food waste, and that increases our biogas production. Currently, we produce about 60 to 70% of our plant power demand. With increased, we could, bridge that gap. We're also looking into some other innovative technologies to basically reach to our, energy neutrality. so we can become energy self-sustainable.
Great. And then so the waste is just as an input, where is it part of the sewer stream, or is it?
So it is it could be source separated organic. So we are our sister agency, South Bayside Waste Management Authority,
Yeah.
WMA. We partner with that. They collect all the the food waste rejects from dailies, restaurants, but they are actually also extracting, or in the process of extracting, organics from your black bins, trash, basically municipal solid waste. And that is what's feeding into extracting this organics. But most of us throw our food into, shouldn't be, but some of the food waste end up in our trash bin. And that is where they are capturing that, extracting the organics and sending it to us, so we can either use that in our digesters, co-digest it, and produce biogas.
And so the end products, besides the I guess energy of the biogas, methane, I guess it's mostly methane.
Correct. Yeah.
And
correct.
and then it would also be, is that biosolids as well?
Yes, it does increase a little bit of biosolids, but again, the biosolids that goes through pyrolysis process turns into biochar, which is a marketable product. It's a commodity as a fertilizer. So it increases that, but the main benefit is increased biogas production, which we utilize in biogas utilization facility and produce electricity. And heat. All our plant heat process, as well as building heat demand, is met by the waste heat that comes from just running those internal combustion engines running on those biogas.
Yeah, so that's fascinating in itself, and all the more reason where you have to pay attention to what's going on and over at Silicon Valley Clean Water. I'm continually amazed when I check in. There's always kind of something. So thanks very much for this update, and I think you connected the drops quite well.
Thank you, Dennis. Have a good day.